Okay, great.
All right, folks, we're ready for the afternoon session. We're starting with Jay. He's a prof over in stats department. We're kind of partners in crime. We teach a data science for Astro class together, and he's an expert in machine learning, a bunch of other things. And so he's going to introduce supervised learning.
Thanks for introducing me, and thanks for the opportunity to giving you a intro lecture on the supervised learning. So I'm not sure about your general background, so feel free to interrupt me in the middle if you have any questions. So the 1 hour lecture will focus on the introductions and some basic concepts rather than some technical details. So feel free to ask me if you have some technical details you want to know. So first of all, I would like to mention the motivation. So as we all know, these days, many decisions are data-driven. So when we say data-driven, we really need to first understand and model the data. So we need to have some kind of a modeling process so that we can quantify the decisions we want to make. So the supervised learning is one of the general framework of modeling the data. And in parallel to supervised learning, there are some other types. These include, for example, unsupervised learning. So unsupervised learning is about, okay, maybe I talk about supervised learning quickly first. It's about you have a supervision label. So the basic concept is that you will have to pair the data in a way you have X and Y, and you want to predict the Y based on X. So essentially, you are building a functional relationship. You learn from the data set and learn how to predict based on a future input X and output Y. Y is your decision result. For example, whether this is a spam email or not, or what is going to be the probability of running in the next couple of hours. So there are many different kinds of prediction. But generally speaking, you have variables X and Y. You want to predict Y using X. So before I proceed, I would like to just comment briefly on other types of learning. So I just mentioned this unsupervised learning. So unsupervised learning is about only using X, no Y, to figure out the structural relationship within X. For example, we collect the students' grades and figure out the clusters of them. And maybe there is a cluster of top performing students, and there is another cluster of bottom performing, right? So we basically want to naturally divide the population according to some quantities, like in this case, the grades. But without giving the Y. The Y is called a label or annotation or human annotation. So without knowing Y, we need to actually find out the distance within X or the correlation within X. And another type, a third type of learning in general is called reinforcement learning. Reinforcement learning, as the name suggests, uses some kind of feedback mechanism. For example, to let a robot walk, right? We got to give feedback. If the robot hits a wall, we assign some penalties. If the robot can actually walk for 10 meters, we assign some rewards. And using this kind of feedback mechanism, we train the model in a way that it can interact with the environment. So that's about the reinforcement learning. There are several other types of learning that are not that sharply different. One of them is called, if you heard of it, it's called semi-supervised learning. Semi-supervised here means some of the data have labels, some of them have no labels. For example, you want to categorize whether this image is a cat or dog. So in supervised learning, we prepare like 1,000 images. Each of them has a associated label, cat or dog. In unsupervised learning, we are only given the images, nothing else. And in semi-supervised learning, we may get 10 images that are annotated as either dog or cat, but the remaining images are unannotated. But we still want to leverage them because they may still provide some information. So that's called semi-supervised. And also recently people talk about the weakly supervised learning. So that generally refers to the case when the annotation, the label itself, even provided by humans, are not reliable. Maybe right, humans have different opinions of the same object. So we actually cannot have ground truth well defined. So in those cases, people generally refer to as weakly supervised learning or weak supervised. Okay, so we talk about supervised learning because this is perhaps the most important, most widely used type. And here, the third category is the commonly used algorithm, including linear regression, which we will talk very soon, logistic regression, which we will talk, decision tree, we will talk, random forest, we'll just briefly mention, and support vector machines, which we will briefly mention, and neural networks, which we'll also briefly introduce today. So as you can see, there are many choices. If you use packages, usually people don't write code from scratch, just use packages. You still have to make a choice, right? So this is the part that we want to learn. We want to have understanding when to use what algorithm, and also how to properly understand the limitations for each of them. Okay, so first of all, we talk about the two general categories under supervised learning. One is called regression, the word called regression. And another is called classification. You see the first word, classification over there. So there are actually two general types of supervised learning. So we will first talk about the regression. What is about regression? It's about y being a continuous variable. So for example, we want to predict the average salary or the expected salary once you graduate, given your basic information, for example, education level or domain of study, right? Different aspects. So so when we talk about the continuous variable, what is the unique aspect of it? Usually it's just continuously valued. And when we set up the model, we would typically assume from negative infinity to positive infinity. But there are some cases where we know that it must be positive, such as from 0 to infinity. So in those cases, we can also properly model the regression in a way that we enforce the outcome range to be reasonable from 0 to infinity. So there are different techniques of regression. So we'll just start with the simplest linear regression. So in the linear regression case, y is just the linear function of x. Okay. But you may say, okay, given the data is clearly not a linear relationship, maybe the data, maybe we see a scatter plot between x and y. It's not a perfect line. There are many points around and it's not clear what it is. So in that case, we may just simplify the problem as it's still a linear function. So y is still a linear function of x, but plus some noise term. The model would then become a stochastic or statistical model. When we talk about statistic, it means we account for the uncertainties. So y equals a times x plus some random effect, epsilon, right? So this random effect is random in the sense that it can differ even for the same individual, for the same x. For the same x, when you observe multiple times, you see different noise and you see different fluctuations along the linear line of x. So therefore, the linear regression is not really a linear function. It's actually a linear function plus some random term. And when we estimate, when we model the data, we actually try to estimate the linear coefficients along with the variance of the noise. Right? We try to understand what is the distribution of the noise together with the linear function itself. So that is linear regression. Any questions so far? Okay. So the second is about the ridge regression. Yeah, I will just postpone the logistic regression later. So the second is about the ridge regression. Yeah, because of the limitation, there are some audience on the Zoom. I'm not going to write on the whiteboard. I'll just try my best to explain the equations. So in the ridge regression case, it's still a linear function of x plus some noise term. The only difference is that we have more assumptions regarding the noise. And therefore, when we estimate the coefficients, the procedure is a bit different from the simple linear regression. So in the simple linear regression case, there is usually something called the ordinary least squares method. So what it does essentially is to project your observed y onto a linear span of the x. And that projection is your fitted function. But when we have this kind of technique called ridge regression, it's not strict sense doing a projection. You actually try to also regulate the L2 norm, the length of the coefficients. And why do people do that? Because people sometimes want to tackle this so-called overfitting issue that I will also talk later. If you have like 10 data points versus 10 million data points, and you want to fit the same model, the story is not the same. You have 10 points, and it's very likely you encounter overfitting issue. The noise can be huge. You just simply do not have the sufficient data to give evidence what is going on. Right? In that case, you may not want your model to be too complicated. So that's why you constrain the L2 norm of your coefficients. So it's not too crazy once you fit it. So that's ridge regression. And how about lasso regression? It's also popular, especially when you have tremendous amount of variable. For example, in the, I'm not sure in astronomy because I'm not working this area, but I once dealt with data from the biology that has actually a DNA array that has like thousands of variables. But there are only 100 patients, right? So you actually have even more variables than your observed subjects. So in that case, how do you run this projection? Because the ordinary least square will not be simply not be allowed. It's a ill positioned problem, linear problem. So in this case, people use some technique called lasso regression. So it's just the name, which again constrain your solution within some particular space, such that the L1 norm of your coefficient is very small. They try to actually, again, regulate your solution in a way it's not too crazy. And also people try to understand why this is good. And people empirically found it's good and have some theory, have a lot of theory actually, to understand when this works. So there is actually a comprehensive literature behind the rationale, but it's not always working. So when you use it, you got to use it with caution because of the limit of the course. When you truly use it, it's still better to check the documentation when it is preferred. I would say, generally speaking, it's preferred when you have a large amount of variables. And also you believe the relationship is somewhat linear. And once you use this lasso technique to get the solution, also try to have some kind of interpretation, whether from your domain knowledge is truly significant. Or you just add some dummy variables. You just fake some, fake data into the data set and see whether it actually, ignore that. If it selects that, then perhaps it's a problem. That indicates the untrustworthiness of using this technique. Yeah, there are many ways to try to make diagnostics. Right, so this is about the commonly used linear regression techniques. But how about nonlinear? Because in the real world, it's hard to believe everything is linear. So when we talk about nonlinear methods, there are generally two directions of thoughts. The first is that you develop some nonlinear methods. So we will talk some of them very soon. So the function you will fit, the relation between x and y, is by nature nonlinear. The second general direction is you still cast it as a linear problem. For example, you think the y is a polynomial function of x with some degree of polynomial. It can be maybe degree 10. That is already very nonlinear, right? And then you have terms like x squared, x cubed, up to x to the 10, right? And then you fit a linear model because the polynomial is essentially linear combination of x to some power. Right? So essentially it becomes a linear problem. Certainly if you have multiple variables like x1 and x2, you will need to consider the interactions like x1 times x2, x1 squared times x2 cubed, something like that. So it can be very complicated. Your model can be complicated. So that's why we need some kind of a visual explanation and diagnostics and also selection. So the next three components are also important. It's not that we pick up some package and then we run it and then we are done. So first of all, it's a good practice to try to visualize it, even though it can be difficult if you have like 100 variables. It's still helpful to at least marginally see the relationship using scatter plot. So you plot x versus y, or x1 versus y, x2 versus y, and see at least marginally whether it's almost linear. What if it's not linear? Then you consider nonlinear methods. And then how do we fit? It depends on the methods. If it's cast as a linear problem, we use the linear regression methods like minimizing the sum of squared errors, which actually is linked to the ordinary least square I was mentioning. If it's a nonlinear method, we use a nonlinear way of modeling. So we'll briefly mention some of them. And then once we get something, we can always get something if we write codes. The thing is whether it makes sense, right? So we have to do some kind of diagnostics. There is a whole literature instead about diagnostics. There is even textbook called regression diagnostics, how to make a reasonable diagnostic on regression model. So it's a huge topic. But briefly speaking, the diagnostic tools about how to either visually or quantitatively measure the deviation from your assumption. So for example, you assume your y is a linear function of x, right? Roughly. So once you get that linear function, you calculate the y minus fx for every data point. So actually you get a bunch of residual points, right? So by your assumption, the residual should be noise. So it should be centered around 0, right? It should be up and down fluctuation around the 0 line. But if it's not, if it's clearly some kind of cosine pattern, or it is like a monotone line, then something is wrong, right? Maybe you should have specified a more nonlinear model. Or maybe your assumption of the noise being what they call homogeneous is not good, it's not right. The noise are not identically distributed. The noise are very subject driven. So every subject has a very different noise level. In that case, you may need to revisit your assumption and then model again until you are happy with your results. Okay, the last step is about selection. So why do you need a model selection? Because we don't know what model to use, right? So in practice, we will just try maybe 10 different models and see which one of them gives the most reasonable diagnostic result or prediction result. So for example, you may try to predict the salary and you develop some cool model. What you could do is that you calculate the so-called mean square error, that is the square, sum of the square of the y minus fx, right? So use that to measure the average deviation between the true data you observe and your fitted data using your model. So if you found that your MSE, the mean square error, is very large, even larger than using a trivial prediction. You predict the salary to be the average salary, say a constant. You found that your prediction error is even larger than that, then that means the algorithm definitely is overfitting. It's not good, right? Something is wrong. But if it's actually better than some simple naive baseline, you may still wonder whether I can do better. Then you try 10 different methods and select the one with the smallest error, right? That is one possibility. But even doing that, you may still not be happy because maybe the best performing model still fails your visual explanation of diagnostic. Maybe there is just some part of the data that is not explained well. So in that case, this visual diagnostic can actually guide you to develop a more sophisticated model. So you just create another model and then re-evaluate, and then you redo the selection. And maybe during this process, you invent something new and cool, right? Some new model. The new model always comes in such a way that you actually have some insights of the data, why the existing model cannot do the full job. Okay, so this is about the general pipeline of having the regression analysis. Any questions so far? Anything you want to ask? Okay, let me just check the Zoom. There's a chat box. Michael, can you help me check whether there is a comments on the chat box? Yeah, I didn't see the Zoom. Okay, sure. Okay, so next is about classification. So the only difference between classification and the regression is that the Y is a categorical value. It's not a continuous value. So for example, I predict whether the email is a spam. I predict whether that observed object is what I'm interested in, like yes or no. Or maybe I categorize the object, whether it belongs to type 1 or type 2, type 3, so on. Basically, your output space is finite. So that is only cosmetic difference. So I would say in general, fundamentally, there is no essential difference in terms of algorithm, evaluation, diagnostics, and so on. So they are essentially the same. It's just when we look at the equations, they may look different. The reason is because when we do the categorical, when we model the Y, that is a categorical variable, we typically use probability. So we say with probability 0.9, it's a spam, right? We don't say directly it's a spam or it's not a spam, because that does not take into account the uncertainty. Sometimes we also want to understand with what probability it falls into some category. Yeah, that's why many times you will see that your prediction result is not a categorical variable itself. It's actually a probability of being each of the possible categories. Okay, so there are some standard algorithms. The first is about logistic regression. So I would say it's essentially a linear regression, except that it's the linear function of x is not y, because you can imagine if x is the salary, if x is any variable, fx can take any values within negative infinity or positive infinity. There's nothing to do with the category. There's nothing to do with the probability of the category. So you got to actually transform the fx, the linear function of x, to the space of 0 and 1. So what people generally do is to use this so-called logistic regression. So logistic regression is such a cute function that will actually map anything within the real line to 0 and 1. So what you do is that you map the probability of the y being, for example, a spam, which is a value within 0 and 1, back to the real line, negative infinity to positive infinity. And you equate that as fx. So fx equals inverse logistic probability y equals some category. Okay, so this is what you typically write. So the essence of it is still a linear function problem. We still want to estimate the linear function. There is another popular algorithm called the decision tree. So the decision tree works by formulating a nonlinear function of x so that it will mimic the probability of y. So I will just visually show that very soon. And also neural networks. So there are many kinds of neural networks, but they are not magical and they are not that deep. What essentially they are doing is that it's a particular type of function, a nonlinear function. It's not linear. It's just some weird function that is visualized as a connection of neurons, but it's just a function. So how do you evaluate the performance? So in the continuous case, we usually use mean square error. So in the categorical case, because it's category, it's discrete, many people use accuracy. For example, what is the accuracy of correctly predicting it's a spam or not, right? So basically, I calculate the frequency of not being able to correctly categorize. If it's a spam, we say it's not. Or if it's not a spam, we say it is. Both are errors. We just calculate the frequency of making such errors on some test data set and use that as accuracy, or use that as an error rate. The 1 minus error rate is accuracy. So the precision and the recall are basically more detailed information. Like if it is a spam, what is the proportion of categorizing it as not a spam? Or if it is not a spam, proportion of categorizing it as spam. Try to have a better understanding of the two types of errors. And area under the curve is also popular. It actually plots the two types of errors on a two-dimensional plane and try to visually see how well your algorithm is performing compared with other algorithms. Okay, so I was just using some pictures to illustrate some of the important points. So we just mentioned that in the regression setting is the simplest model to consider linear regression. And in the simplest setting, we only have one variable x and one variable y. And you just see something like this. And then you try to fit a line that is cutting through the middle of the points. And there are different techniques to get this line, like the ordinary least square or the lasso or the ridge regression. Those are all different techniques to get a reasonable line. But how reasonable is the most reasonable? You would need to use diagnostics to check which one gives you the best performance, smallest error, or which one gives the reasonable visualization that matches your assumption of the data. So you can make a story when you publish an article. Okay, so this is a logistic regression. So in this case, the X is hours of study and Y is the probability of passing the exam. So the training data, the data we use to model or train the model is basically the pair of student hours, student working hours, and student whether or not passing an exam, right? So what we do is that we collect the data and then estimate the logistic regression model parameters, and then visualize something as shown in the blue curve here. So the black dots are the original data, the data we collect. The blue curve is the model we fit. So this curve shows that if we study around maybe around 3 hours, the probability of passing is around 0.5, let's say. And you study like around 5 hours, the probability of passing is very close to 1, right? So you can interpret the result in a way like this. And this is another type of modeling called a decision tree that we briefly mentioned. So this decision tree is actually a type of nonlinear model that is most popular before the deep learning. In the last century, it's very popular. So what it does is that we try to visualize the function and also operate the estimation of the function as a tree structure. So we first decide whether particular variable x1, say the hours of study is within T1. If it's yes, we go to the left branch. Otherwise, we go to the right branch. And furthermore, if we have some other variables or even the same variable, we can make a further decision, right? Whether the students have enough hours of sleep, if it's less than 7 hours or not. And then we go to the left or right branch. And we just keep going on, right? And until we actually mathematically divide the space of x1, x2, and so on into many small chunks, right? Each small chunk will actually correspond to one of the tree paths, right? Yeah. And when you make a decision for new input, for new student, you just go through the tree. Whether the student sleeps 5 hours, whether the student sleeps 7 hours, whether the student actually studies more than 3 hours, and so on. You make a sequence of condition, if-else condition. And then until you reach to the bottom, which we call leaf node, which corresponds to some small area in the space, in the data space. And then you make a decision there. So each area will be associated with one unique category. Fail, not fail, 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 not fail, something like that. Right? So essentially, mathematically speaking, the decision tree is a technique that uses piecewise constant function to approximate a realistic complicated function and train using this kind of greedy decision, stepwise decisions. So we actually need to train those nodes like T1, T2, T3, and how actually we divide at each step. So these are all part of the training, the model. So this is a decision tree. But when we interpret it, people like it because the decision tree is really straightforward to interpret. So people like decision trees, but people barely use decision trees in reality. The reason is that it's very unstable. So if the data are perturbed, so if you have if you remove or add some students, the results can totally differ. The tree can be a very different look. So it's still, in that sense, not interpretable. People may just say that although you can interpret this tree, your result is not trustworthy because it can easily be manipulated into another tree, right? So people start to look into so-called ensemble methods. Okay, so there is a question from the chat asking whether the decision tree overfit data. Yeah, that's what I was talking. Because the decision tree tends to overfit the data, and it's often not so clear when to stop the branching process. So it can cause very serious overfitting issues. And that's why people start to look at the ensemble methods. So the first ensemble method, or first of all, let me just explain. The ensemble here means you have a collection of individual small models, and you just combine them and make it a so-called ensemble. And so ensemble methods is basically not a new method, but a systematic way of combining small methods or small models. So the first ensemble method is called the random forest. So this is a method that will just combine many individual trees. So how do we combine them? So what we do is that we just randomly pick up subsets of the training data. For each of them, train a tree. So then we would have, if we repeat 1,000 times, we get 1,000 trees. So it becomes a forest. Right? And then when we predict if it's a regression task, each of the tree will produce some Y. We just take the average of those Y, just like voting. And if it's a classification with categorical output Y, we just collect the frequency. So who votes this category? And then which category gets the most votes? And then we just choose the category with the most votes. So it's again, just a majority voting. So random forest is basically a decision tree plus randomization of the data plus a voting mechanism. So this is random forest. So random forest is good. It's actually very commonly used still today in industry. Part of the reason is that it's first of all more robust than single decision tree, less likely to overfit, and often gives good performance. And also computation-wise, it's very easy to parallel compute because each tree can just be on a separate node, CPU node. So you can actually run simultaneous. You don't need to wait for the first tree to complete before you run the second tree, right? So in today's age, where the computation is everywhere and the hardware is limited, it's actually very important to find the computationally efficient but still good performing methods. So random forest is good. The second is called bagging. Yeah, so the bagging is about is another way about combining trees, but usually it's I would say less likely used compared with random forests. So I wouldn't suggest that in practice. So bagging often is like used together with random forest, I would say. So what bagging does is try to randomize the data and then introduce variations in your modeling results, and then you later on using the voting mechanism to combine them. But I would actually, during my description of random forest, I already implicitly use the bagging technique. So yeah, I wouldn't use bagging alone. I would say the second, the most widely used ensemble methods is called boosting trees. So boosting trees is actually boosting algorithm plus decision trees. The boosting algorithm is a general algorithm that try to augment your existing model in a way that you sequentially add more and more trees or add more and more what they call weak learners, weak models, so that the final model is very strong. So technically speaking, what it does is that you first have a decision tree and you fit it and see which area isn't fit good, fit well. And then you fit the second tree with some kind of a weighting so that you focus more on the area you didn't do well. And then the third step, you fit another tree that take care of the rest, right? So eventually you have a sequence of trees that will do better and better. So compared with random forest, I would say the accuracy is generally better, slightly better, but according to my personal experience. But the computation is much heavier because you need to actually run it sequentially, right? Yeah, there is a question I will answer very soon. So for both of the methods, the random forest and boosting trees, they actually handle the overfitting well because they introduce multiple models and they're using the average to smooth out those large variations. But I would say the boosting generally suffers more overfitting because you still need to, cut off the number of trees that you are sequentially adding. But random forest is generally more robust to that. Actually, the more the better in random forest case. The more trees, the better. So that's different. And there is another nice thing about the feature called the feature importance as a byproduct of using either random forest or boosting trees. So the feature importance basically is a quantity that try to tell you variable 1 is most important, x1 is most important, x2 is less important, x3 is useless, something like that. So how do they tell that? Well, if you look back into the decision tree, you will see that actually every node there will be a variable showing up, helping you make a decision, right? You just count the frequency. The simplest way is just count the frequency. You see the x1 or x2. If you every time see x1, never see x2, then x2 is useless, right? x1 is important, right? So you just use this tree. And then in the ensemble method, you have more trees. Just take advantage of all those trees to eventually come up with some metric. So this will sometimes used by people to interpret your results, such that in a way such that you not only predict well, but you also tell the audience that you predicted well because of x1 and x2, right? So that is nice in practice. So the question is about how important is the choice of attributes for branching decision trees. Do we have trees in the forest having different attributes for branch? Yeah. So the first question is how important we use the attributes in branching the decision tree. I'll say, yeah, definitely it's important. So if you have a set of variables, x1, x2, x3, and so on, that actually will contain some important variables, you will realize that later, that those variables are often used to branch the trees. So people generally just start with a large set of variables and then use variable importance to narrow down the scope and then do the further model. from there. And second is whether we need the trees in the forest to have different attributes. Yeah, that is often used in both random forest and bootstrap trees. What it means is that for every tree you build, you actually select a subset of variables. You enforce them to be somewhat different. So in this way, you actually introduce some diversity and reduce the risk of overfitting. So next, I'll just briefly talk about SVM, since this is also very popular, especially before the ensemble tree becomes popular. People still use it nowadays, partly due to the nice interpretation and visualization of these results. But it is most in large scale problem, it's barely used, I would say. And so what this method means is quite visually appealing. So what it means is that we have two clouds of points. Here is the triangle, green triangle and orange square. And because it's supervised learning, so we know how to color them because we know the label. So we know this is triangle, that is square. What we only need to do is to find a decision boundary such that we can separate them. So people say decision boundary. Essentially, it's a mathematical object that tells us that within one side of the boundary, we should categorize it as triangle. So with probability larger than 0.5, it belongs to the triangle class. And on the other side of the boundary, it's a second class. Right? So basically, it's a line where the probability of being in each class is 0.5. Okay, I just thinking that way. But in the support vector machine case, because we are not actually building a statistical model, so typically people wouldn't interpret it in that way, but just thinking that, imagine it that way. This line is basically the equal probability line. So how to find this line? The support vector machine will actually provide a loss that you minimize. Okay, I haven't introduced loss, but basically the idea is you find a line such that the shortest distance from one class, from the triangle class, and the shortest distance from the other class, the square class, is very large. The shortest length is very large. So in this way, you maximize the separation, right? So that is the idea. But you may say that what if it's just not linearly separable? What if the data are challenging? They are kind of mixed. So in that case, we need to actually map the data from lower dimension to higher dimension, so that in a higher dimension, it is separable. So here is 2 dimension. But if I make it challenging, I will just plot some triangle in this area and plot some square in this area. Then how do we do it? So what people do is that we just introduce a 3rd dimension, which is the height, and then we lift the orange square along that direction. So in this way, these 2 clouds will sit in the 2 different planes, and then we can easily find a separable line or hyperplane that separates these 2. Right? So it's really important to actually map the original data. So when people say map, they sometimes call it the transformation, the transform or feature engineer. So when we engineer the feature, hopefully they will just sit in a larger, more separable space so that we can actually more easily separate them. So SVM is not only a tool, it actually provides a view of how we think about the classification. So how do we map? There are different maps in the literature, and there are different packages you can use. there are some tools how to automatically actually transform the data. So in this part, I will just briefly highlight the importance of understanding overfitting and underfitting. So what is overfitting? Briefly speaking, your model is too complicated. The data is too small. You only have 10 data, but you have a model with 1 billion parameters. That is likely to cause overfitting. So overfitting means that you fit the data very well because you have a large model. But when you generalize to the future data, which is our ultimate goal, right? We don't want to play well within the current data. We want to generalize well. Then it's going to be fail. And actually can perform really horrible compared with even a naive baseline. So that is serious overfitting. What is underfitting? It is a very small model, too small, to model the complicated relationship within a large data set. So if you have 1 billion data points, but you only use one-dimensional X and one-dimensional Y, maybe you cannot capture all the physics there. So in that case, we have underfitting. So what is underfitting usually shows up in your data analysis is that as you increase the complexity, you will see that your performance can get better. So that means you should continue improving your model, right? So generally, people visualize this overfitting, underfitting issues in a two-dimensional plane, where the x-axis is the model complexity. The y-axis is the generalizability, meaning the performance on unseen new future test data. So generally, you will see that the performance goes up as you increase the complexity. And then it starts to drop at some point if you continue increasing your complexity because your model starts to overfit. So you want to actually hit the right point. Just hit the point where you get the peak performance. You select the right complexity. So how do we do that? Then it relates to this literature called model selection. So you got to use one of the model selection techniques to select. I didn't touch anything. Okay. Yeah, I think I'm almost done here. Yeah, I'm done. Oh, no, yeah, so it becomes okay.
All right. In that case, let's thank Jie. Okay. Good job. Let's plan to come back at 3:15, so 15 after folks.